Okay, so today we're going to do a review, ask questions, go over the practice problem, maybe some things from the homework 4. The general pattern on the homework 4 answers is every once in a while somebody might leave out combining some term or take the derivative and not quite use the chain rule, and so things would get off just a little bit. But those things happen. It's hard to pay attention to all the details. So my recommendation for the exam is to show work. Write things out in stages. So generally, if you set things up correctly, and then there's some combining error, but then you take logs and take derivatives of that, and doing most of the things right, then I can give most of the points, because you're really trying to understand the overall procedure and what we're trying to do with things. I try to write the problems so that they're not so dependent on one after the other. So even if you have trouble getting the MLE, it might ask you something about how would you get a confidence interval for this, or how would you do a bootstrap for that example. So the other parts of that problem, although they're on the same general problem, won't necessarily be so dependent. Right? Solutions for the practice problems in homework 4 are posted. I just wanted to put these up. I don't have copies printed out for everybody. Under the assignments folder, go there. There's all the homework assignments that are there, and then eventually we have a project, but then there's this exam 1 link under there. And so, like we talked about previously, it's chapters 3, 4, 5, and 6. Part of 6, finding an MLE, maximum likelihood estimator, talking about a bootstrap for that, but not so much doing the method of moments or the theory. But we might describe a simulation of how would you evaluate an estimator. Not so much the technical aspect of it, but just generally what is an estimator, why is it a random variable, what properties could it have, without going into a lot of the technical things. So looking at lecture notes, textbook, the homework problems and solutions are posted. So under assignments, if they're all posted there, these are the exam practice problems. You don't need to look at the R code or the data sets, but that's what I generated from there. So let's look at some of the problems. Right? So we'll set some problems up, okay? And then if we want to go through more details, we can do that. Why don't we just go ahead and start in on some of the practices. Right? So it gives you the first practice one. Gives you this density f of x given beta as 1 over beta squared x e to the negative x over beta as a density. There's actually a gamma random variable that probably has a PDF looking something like that for the value of x. It's describing where the observations are going to go. If we have n independent observations, from this density, the joint density of all of them together for beta is the product of those. And so this density gets put in there, and this is becomes a little I on it. e to the negative xi over beta. So all that's multiplied together, and then we can combine. Since there's 1 over beta squared, there's going to be 1 over beta with 2n. There's xi is multiplied together, so x1 times x2 times x3. So that'll be a product of the xi's of the term. And then there's minus x1 over beta in that exponent, and minus x2 over beta. So those get added together. So there's an e to the negative sum of xi over beta. Okay. Right, and we're going to take the logs of that thing and then differentiate. Work out, right? So the log, this is the likelihood for beta. Find the beta that's most consistent with the data we have. And so if we take the log of that, that'll be easier to work with. So beta is in the denominator, so it can be negative 2n log beta. Now maybe that's a little fast to write it out just like that, but it could work out other ways. There's this thing, the product becomes the sum of the logs. The log of the product is the sum of the logs, and then minus the sum of xi over beta. So you could do this one, in 2 steps. You could do, right, instead of jumping to this, there's a, what would you do? I mean, maybe there's 2n log of 1 over beta. And then this one is, there's going to be a log of the product of the xi's. And then that goes to that. So, and then this one, I think you would just kind of go pretty much right into that, so just the log of those. So this would be kind of a steps kind of along the way. And I would go to the next one. However you want to do it, writing out as many steps as you take. I'd probably give you most of a page for doing this calculation, so you can write out details. Then take the derivative of this. Derivative d beta of the natural, or just log of the likelihood. What do we have? There's a negative 2n over beta, and there's a minus the sum of xi. I can't recall it exactly.
Do you have a preference of if we write log versus natural log?
Either way, it's, in your science and other classes, if you're used to writing natural log, that's fine. It's, the default in R for just the log function is natural log, but you can also write ln. That works as well. Negative 2n, and then this is a plus actually, because there was a sum of xi over beta. Right? I'm taking the derivative of that with respect to beta. Since it's beta is -1, you get a negative. Over there, it becomes positive, and then there's a beta squared. Right? And then set that thing equal to 0. And some of these things, when the parameter is in the denominator, you can just kind of multiply through by the parameter or the parameter squared, and that's kind of a quick way to get it out of there. So if you multiply by beta squared, this would be -2 in beta, right? And the beta squared would cancel that one, equals 0. And then you're going to put 1 on the other side, so think about adding that to the other side, 2 in beta, add it to both sides, it would cancel over there. And then you end up with beta as the sum of xi over 2n. And you call that beta hat, maximum likelihood estimator. So you could also write it as x bar over 2, half of the sample average in this case. On the practice problem, I put the method of moments ones there. I don't plan to ask about method of moments, but they end up getting the same estimator actually, these So that's it, right? On the graph. But any questions about it? So I'll come up with another one. It won't be overly complex. It'll be something that you actually can get a solution written out. It won't need to do grids or other things. But there's plenty more. So with this log, this likelihood function, or its log, right, is a log likelihood of beta, right, is a function, right? So it has a value for each value of beta, and I graphed it on the practice problem, and it kind of goes up steep here and kind of goes out kind of like this. Right? And so where's the maximum likelihood estimate?
Highest point.
Highest point, right? So say that's the highest point. What's the value of beta that does that? Right? So you'd also want to map this down to this point. Beta hat is a value on this axis, and it produces that highest point. So this value of beta hat is the value that would correspond to the maximum, right? So this maximum is log L evaluated at beta hat MLE, is that height over here. The other thing you can illustrate with maximum likelihood is that the derivative here, at this point, the derivative of the log L of beta d beta, right, is 0. That's where there's the tangent line is flat and it's a maximum. If you take a second derivative, we haven't been doing that, it would be negative, so it would be concave. You could do it. We will be taking second derivatives, but not until Friday. That's most of this one. And then part D was describe a bootstrap for estimating a standard error of your estimate. And maybe I'll go to the solutions. So one thing I'm thinking about these, describing the bootstrap and permutations and things like that, is think about practicing writing down the steps. Like which steps would you need to write down to make it clear? You could follow my examples. You can phrase it your own way as well. You can look and see how the book writes it down. Kind of pseudocode, list of outline of things. You can write it in sentences, or you can write it in numbered points, as you wish. So this one, so there's the picture, right? So this one, I wrote to generate a bootstrap sample by randomly sampling from x1 to x10 10 times with replacement. Right? So in this particular problem, I said there were 10 values. Right? So you want to say we're going to sample from those 10 values 10 times with replacement. Right? We're going to compute x bar star. Maybe you would say that the 10 values you get out here would be x1 star, x2 star, up to x10 star. Compute x bar star, and then the MLE. Right? Take x bar star divided by 2, and that's a new beta hat. And repeat those two steps a bunch of times, and compute the standard deviation of those beta hat stars. Right? It's specific, right? It's fairly general, but it's also specific in mentioning the 10 times for this problem, and this is our estimator we're going to compute. Yeah.
So if you just say describe like the bootstrap procedure, that's all we would have to do is just write out.
Pretty
the
much,
steps.
yeah,
Okay.
yeah. I mean, we don't have really a way to do computing
Yeah,
and
okay.
things like that. So I didn't put on there, but I thought it was a follow-up. If the sample size n is 10, why do we use 10,000 bootstraps? So let's just think about that. Read the answer. So there's this little n and capital B, right? So sample size and bootstrap sample size, or bootstrap numbers. Why do we make it so big? What does the bootstrap try to do for us? Yeah.
It gives us like all possible samples from the sample set.
Yeah, so we could, well, so if there's 10, right, if we had to choose 10 times for this with replacement, there's really 10 to the 10th different samples. There's not really that many because there'd be some duplication, right, if you got there'd be overcounting, but it's a huge number. Right? instead of doing all that, 10,000 is a pretty large number of sample points to estimate the sampling distribution. Beta hat has a sampling distribution, so with 10,000 samples like that, it'll give us a lot of information about the sampling distribution. So we can get the standard deviation of it, we could get the percentile ranges of it, right? So you see a pretty clear picture of what that is. Right? If we made this 100,000, would it make our inference procedure any more precise?
Yes, but not much.
Well, so it's kind of for some things it'll be more precise, right? So 100,000 would help us know about that sampling distribution. But are we going to get a better determination of beta? No. Why don't we really gain information about beta by doing more bootstrap samples? This was this thing that we really only have 10 points. So the sample size is really 10. The accuracy, the precision of the sampling distribution is really determined by the sample size. And all we're doing with the bootstrap is trying to describe that sampling distribution. So yeah, we need to describe it with a lot of points, but it doesn't make it narrower or wider very much. But it would help you know something about that, I guess. Anyway, that's the follow-up. Right? There are 10 to the 10th possible bootstrap samples. And we ran these 10,000 to represent the distribution of the sampling distribution. And from that sample of 10,000, we can estimate the samples. So that was one practice. There's a couple other practices that are kind of related on the next part. Any questions on that one before we go? So on this next one, so these this next one could be a little bit confusing, and I'll try to avoid that in that. But in this case, x is something called a negative binomial. Kind of like counting successes, but this is counting the number of trials until you get some successes. So you could keep going forever if you're very unlucky. And there's a parameter r, which is like sample size 100, and then a proportion p that's in there. And so the probability that x equals some value is x minus 1, r minus 1, a combinatoric thing up here, p to the r, and then 1 minus p to the x minus r. So we really kind of only have one observation when it's presented like this. It's the count of the number of trials. So you're going until you get 100 successes. So it's kind of like 100 trials, but they're all added together. So in this one, right, the MLE, so we observe, this number of trials to get our successes. And so we have this density. So this thing by itself is the likelihood to repeat. Right, so this wording of this one just is a little bit funnier. But if you do this one, what do we do? If that's the likelihood, well, we're going to take the logs of it and take a derivative with respect to p and set that equal to 0. We're maximizing it. So the log of this likelihood, in this case, there's a log of this combinatorics thing, and that's going to go away once we have a derivative. So it's not terribly critical to get a clear understanding of where that comes from right now. Then there'd be r times this one, and then x minus r times the log of 1 minus p. We don't set that equal to 0. We take the derivatives and then set the derivatives equal to 0. A couple of times people didn't take derivatives, they just set it equal to 0 and solve for something. Got an answer, but it wasn't quite the full procedure. Could be just kind of rushing or just forgetting that step along the way. But. So, this thing with respect to P, there's R over P. The log of P is 1 over P. This one has an x minus r multiplier, and so 1 minus P comes down here. But then you have to take the derivative of this one. Yeah, so that's where you get a negative. And you set that equal to 0. But be careful if there's a chain rule to do, and then you set that thing equal to 0. The negative in here is because then you can add this to both sides, and you'll get P on both sides, and can work around it. Right? But any questions about it?
So
Yes.
How did you know that, L of P was just that equation? Like, why?
So it'll probably be phrased more like number problem 3.
Okay.
Right? The 3 is phrased as in a certain number of independent geometric random variables. Right? And so each one is one success and then a number of failures. And so that one would be would look more like what we've done. But anyway, you solve for this, that equation, set it equal to 0, and P hat, this is the one, there it is. Turns out that P hat, once you solve all that, is this R over X. And it tells you that we had tried to do 100, to find 100 people, they had to search through 150. So X is a 150 number out of 100 trials that's specified in the district. So it's about 2/3 as the proportion once you solve that. Yeah.
Are there certain distribution functions that we should have memorized down pat, like the ones we've more?
It'll be kind of presented like we like it's on these practice sheets, where the density that you need is listed on there.
Okay, I was just wondering.
Yeah. It's exponentials, betas, gammas, some version of that, maybe with one of the parameters. If there's 2 parameters, I'll put one at a certain value. So it looks like a variation on one of those themes. But yeah, the something from Appendix C or something similar. Right?
Okay.
But and I think you've seen the range of things that you combine, either x or x to a power, or e to the x or e to the negative x, that type of thing gets combined. So then this problem asks, there's a log likelihood for P, illustrate the MLE. So it's again, it's the important part. So if this is the log likelihood for P, or it could just be the likelihood for P, either one. The log likelihood sometimes this one looks something kind of like that. And we want to find the place where it's 0. That's where the log of likelihood, where the slope is 0 at that tangent place here. And we map that down to here, and there's our P hat MLE. The point that leads to that maximum is what we're doing. And then describing a bootstrap.
So for this one, we kind of only have one.
Observation.
Yes.
So, you would have, there's 150 people. 100 of them are knowledgeable, and 50 of them are not knowledgeable.
So you
So it's kind of like you have 100 ones
and 50 zeros.
and 50 zeros.
You bootstrap
and you
that.
bootstrap that. Yeah. You could do something like that. But anyway, you can think about describing the bootstrap in that problem. The third one is basically equivalent to that one, but it's geometric. X is geometric with the probability P. So X counts the number of times until you find one person. So the probability that X is P, and then 1 minus P to the xi minus 1. And if you do R independent trials, you're going to get x1, x2, and then up to xr. Choosing it this way matches it up to the geometric, right? If you have independent observations, we can do what we typically do. Right? What's the probability that we have the x1, x2, up to xr, all those observations? The product I going from 1 up to r of the density, p, 1 minus p to the xi minus 1. So all of this is inside the product there. So that everyone has a p, so there's going to be r of those multiplied together, so they can make p to the r. And then the 1 minus p, what happens with that? Right? There's an x1 minus 1, x2 minus 1, x3 minus 1. So when we add them together, we end up adding xi minus 1s all together. And so there's a p to the r, 1 minus p, times this is the sum of xi, minus r. Right? If you split it, if you break it, right, this affected one of the homework problems. There was an xi minus 1 up there, and then some people wrote the sum of xi minus 1 instead of in that problem. So when this exponent is up here and you distribute it, it becomes, there's how many ever this sum is. Here we're doing r to match up the other problem. But anyway, that ends up being the likelihood for p in this case. It looks just a little different from the other one because it didn't have that combinatorics in there. Right? But the estimator is going to end up being quite the same. But I'll let you look at the solution on the web and go through that and ask questions about that one if you have questions. So what were the other questions? The other one touched more on the other chapter. Any questions?
So we're not really worrying so much about method of moments for this?
We're doing, yeah, you don't have to figure out a method of moments one for this. I just had that written as part of there and kind of just illustrated it, but it'll be focused on the maximum likelihood going through these different steps. Right, so what are the problems that are here? This one. Touch on other parts of the class. So there's that. So this fourth one, there's 4 cherry tomatoes plants and 3 grape tomato plants in a garden. The harvest from these plants is weighed. So in the summer, the 4 cherry plants yield that many pounds of tomatoes, and the 3 grape tomatoes. So the cherries are little red ones, and the grape ones are a little bit more elongated. A little different flavor, right? And so those are the things, right? State hypotheses, we're comparing these types of tomato plants. Estimate the average difference, describe a permutation test for evaluating a hypothesis. And there's actually 35 possible permutations, and those are the ordered values. And then use that to make a conclusion, right? A p-value. What hypotheses would seem to make sense? Two tomato plants, or the 2 types. Right? You could have a hypothesis.
Average yield is the same.
Average yield is the same, yeah. Right. So this 4. If you write it in symbols, you can use, this is the average yield for cherry tomatoes. It's the same as the average yield for the grape tomatoes. You can use symbols, but try to define the symbols in some way. Right? If you just write mu1 equals mu2, I kind of get the idea that you're comparing the two groups, but it'd be nice if you said that this is, you know, for the average for this one, and this is the average for this one. It's fairly standard symbols, but it's good to put it in context, and it doesn't take that long.
So you prefer for us to do both, or just write average yield for tomatoes?
You could just write the averages is fine. It is the symbol that we're, you know, would use for that type of things in the models, right? And then an alternative, you know, that they're not equal to each other. And we're going to calculate the average for the cherries and the average for the grapes. So for the exam, having a calculator can help you do some of those calculations. I don't anticipate there being a huge series of numbers to type in and calculate, and maybe I'd give you some summary statistics. You know, if this was not based on 4 and 3, but 40 and 30, I'd probably give you the averages. Something like that, right? So this one, the solutions I've written out. So yeah, so you can define it some way. The cherry tomatoes averaged 8.9 pounds, and the grape one 7.5. Those are the sample sizes. So the average difference is 1.4 pounds. How do you do a permutation test? Remember, this was the two groups, and under the null hypothesis, if there's no difference, we put the 7 observations together. Right? And then take 4 randomly. Well, what if these had been the cherry tomatoes and the others had been the grapes? Right? So you randomly take 4 and compute this. Use the other 3 and compute this. To some degree, because I talked about the C meaning the cherry tomatoes and the G meaning the groups, I haven't written out explicitly all the exact codes for what those things mean, but there's enough there that it's pretty clear to do. Right? It's better to write a little bit more and be clear about it. Take the difference, repeat these things 1 through 4 many times, and calculate the percent of the time that the differences in step 4 here are greater than or equal to 1.4 pounds. Right? And so the 4 and the 3, because there were 4 and 3 in the groups, makes it a little specific to that. Mentioning the 1.4 pounds is specific to that. So it's the general algorithm, but it's a little specific. Yeah.
So for a permutation test, you take all the data points and basically disregard which group it was in at the beginning?
Mm-hmm.
Okay.
Yep. For this one. And then we reject the null hypothesis if that percentage is small, like less than 0.05. And in this case, there's 3 of them that are 1.4, and then two that were bigger than that. There's only 37 or 35 combinations, because 7 choose 4 is the same as 7 choose 3. So 7 times 6 times 5 over 1 times 2 times 3 is 35. There's actually only 35 ways to divide those into 4 and 3. It's not that big of a number. And 3 of them are at least as big as that. We would almost have to get the biggest one, like all the tomato, the one type of plant would have to be bigger than the other type of plant. But they're not. So it doesn't quite end up being significant in this very, very small sample. But it's kind of on, 3 out of 35. 10%, 1 out of 9%, something like that. So it's not, any of those, that's fictitious. I don't really know if it is. But I do grow those type of tomatoes.
This isn't experimentally gathered?
No, and I didn't actually weigh the tomatoes, and I just put them all together. So anyway, that would be the significance for that one, right? Another thing we did is with normals. So here's a different one. Suppose cherry tomato plants average 8.5, with standard deviation of 15. The gardener sows 10 plants in the garden. Suppose the plants are separated from each other, so they're independent. Not that they often are. If you plant them close together, you can kind of support each other. And the way the yields are approximately normally distributed. Right? What's the sampling distribution of X bar? Chapter 4 talked about the sampling distribution. Right? So this could be phrased as something specific like this. Well, by the central limit theorem, or taking this, that it's normally distributed right? X bar should be normally distributed, or close to it, with this average. And the important thing is that the standard deviation is no longer 1.5, it's 1.5 over the square root of 10. So it makes it smaller. And if you have your calculator, right, so this would be the new sampling distribution. And so the standard error is this 0.474 pounds. Well, that would be pounds, because everything's in pounds. And so it asks, what's the chance that your average is greater than 10? Well, you don't have a normal table, so I'm not going to ask something where you have to give me an exact value. But if you take the 10 minus the mean and divide by the standard error, you get a z-value of 3.16. And that's kind of far out, right? It is small. It's actually about 0.0008. So some impression of the normal. Or you could draw a picture that the standard normal graph. So the normal sampling distribution in this problem. For X bar. Here's X bar. It's 8.5 in the middle. And then it's about a half pound, a little bit less. So if you put 9.0, 9.5 up here, I know it's not exactly half a pound, but, and then down here a couple, 8.0 and 7.5. Most of the values of X bar you'd likely see around here. This thing was up here above 3, so it would just be smaller. Or the standard normal, right? Once you standardize it by subtracting the mean, this is usually plus or minus about 2. And then kind of 1 and 2. And then we're out here at 3 or so, 3.16. So thinking about it that way, plus or minus a couple standard deviations. If it's much more than that, that's pretty unusual. So it does a little bit with sampling distributions there. And now we have some potato plants that are, how many potatoes grow underground. Describes how to use a bootstrap simulation to use a 95% confidence interval for the average number of potatoes grown from that type of plant. And then here's a histogram of bootstrap. So where's the confidence interval? How do you take that into a confidence interval? So this, here's it more written in sentences. If you have that graph, if you can draw on there the intervals, it gets and express that those 2 points in terms of the x-axis give you the endpoints. They're the kind of central 95% of the sampling distribution. You're pretty likely to have the actual average covered by that interval. And that does something with that. But again, there's this kind of description of the algorithms that go into it. The other things that might be relevant to ask is what impacts that sampling distribution. What's going to happen if we didn't have 12 potatoes but had 120? Right? How's that going to change the sampling distribution? Yeah.
Why is that not the 250th and 970? Because isn't that a 90?
Oh, this is like a 90th. Yeah, so this would be 250, right?
Yeah.
Sorry. Yeah, that'd be better. 250th and 9,750th would have 95% in the middle. Yeah, I just kind of did a mental. That would more directly answer the 95% confidence interval. If you just set a confidence interval, you could say I want a 95% confidence interval, or you could say I can want a 90% confidence interval, and it can give me whatever corresponds to that. Good catch. But as the sample size gets bigger, 120, or how's that going to change the sampling distribution?
Will look more normal.
It likely will look more normal, right? If there were some potato plants that are really small or very big, right? In were 120 instead 12, how was the sampling distribution of X bar change? Because of the central limit theorem, it's going to be more normal-like, more closely normally distributed. If the original potatoes, their counts, they're integers, right? Sometimes when you're digging with your shovel, though, you cut one in half, it doesn't really count as 2 potatoes. But so it's just a number of potatoes, and so they're not normal by itself. It might be kind of bell-shaped, but at integers. But if you average things together, you can get decimals. And the more you average together, the more normal and smooth it's going to look. Right? How else will it change? The other things that are important are things like the mean is should still be this 8.5 pounds. Right? Should be still something the same, but now narrower. It was 1.5, but now over square root of 120. So it should be quite a bit narrower. Right? So the chance of being over 10 pounds from a sample of 120, it's just never going to happen because it's just so close. Right? So that gets at a few of the problems that are there. Any additional questions about any of the practice problems, or? Yeah.
Did you say you were going to give us like some portion of like an R code or something like that? Or like what would that look like?
So some of it would be the, I could give you something like these, graphs.
Okay.
Or here's just a list of values from the permutation.
Okay.
To describe this, so maybe I would give, like the maximum, minimum, and maybe every 10th percentile, something like that.
Yeah.
So then you could turn that into a 90% confidence interval, or 80, I guess, something like that. I've not put on anything in here really with cumulative distributions. Right? So if you have something that had a histogram of values, from the bootstrap, kind of like this, and maybe a few going out, something like that, that the book did have this cumulative distribution function. So it's the probability that you're less than a value of x. And this thing kind of starts out, then it's kind of going to come up here a little bit faster, and then kind of go out slowly. Right, up to 1. And this thing was the probability that x is less than or equal to some value. Right? So it's possible to use a cumulative distribution function. Let's say you did 10,000 bootstrap samples. I could do the cumulative distribution of those, kind of corresponding to a histogram, and say, where's the 95% interval? So graphically, you would kind of take the 0.025 place here and the 0.975 place here, and map it over, and then map this down, and map this down. And we'd end up with kind of an interval. It's not drawn too well to correspond to that. But anyway, that was another thing that was done in R, to make that a particular graph. We didn't do that as much. Mostly we just took the histograms and found the cutoff point. But it could be a way to put it on the exam and do something like that. But. Yeah.
Do we need to shade the region too for the CDF?
You could say that this is the interval. Something like that. The distance between these 2 points is 95% on that axis. So, but kind of give me what's clearly a lower and upper bound on the intervals would be good. So let's talk about a homework problem. Right? So I think it was the number 6 on the homework. had to do with that multinomial problem, right? And, reading back over it, the first statement of the first part of that was a little bit incomplete, perhaps. And so people interpreted it as having one observation that was 0, one observation that was 1. There was the 0, 1, 2, or 3 were the option possibilities there. And if you had 4 data points like that, the probability of having a 0, a 1, a 2, and a 3 would be there's 2/3 theta for the first one. There is 1/3 theta for the second one. The third value of 2 had a probability of
2/3 1 minus theta?
yeah, 2/3 1 minus theta, and then 1/3 1 minus theta. Right? And if you had one observation of each, that you would put that would be the likelihood. And you could combine things. So there's like 4 out of 81. You can actually multiply those together. There's a theta squared and a 1 minus theta squared. And you use that as your likelihood for theta. And then you can take the derivatives, or take the logs, take a derivative and set it equal to 0, and you ended up with theta hat as 1/2. Now and so if people wrote that down and went through that process, I could give you credit. I didn't actually mean for there just to be a 0, 1, 2, and 3, but imagine that you had n observations.
I think the genetics one.
And some are 1, some are 0, some 1s, and some are 2. So let's see, we'll call this Q, R, S, and T is the number of observations. I like that numbering system for this. So the number of observations is Q plus R plus S plus T. In independent observations, they come out being 0, 1, or 2. This is like a little table. And so these are the values you can see. And these are the number of times it occurs, or the total sample size is in. Right? So what's the probability that we're going to see Q, R, S, T counts? Well, then there'll be a 1/3. It was 2/3 theta for the first one. There'll be that raised to the Q power. And then there's a 1/3 theta chance of being a value of 1. That occurred R times. And then 2/3 times 1 minus theta occurred S times, and 1/3 1 minus theta, that occurred T times. Right? So if you had multiple observations, and not just one of each value, right, you would have these extra exponents in there. And you would get something that'll have some number out front, but there'll be a theta to the Q plus R. There's a 2/3 and 1/3 out there, but they'll go away once we take logs and differentiate. And then this thing to S plus T. And so if you do the maximum likelihood with this, as described in the solutions, you end up with theta hat being Q plus R over the sum of all 4 of those over n. And in the little data example that I gave, that works out to be 1/2. So the problem, I would have, if I were going to rewrite that problem, I would have said we have this many observations of 1s, of 0s, this many of 1s and 2s, and so on. And it would have been more of a likelihood like we were used to. So if you take the logs of this, we could do that. So this is the likelihood of the theta. And if we take the log of that, there's that constant thing out there, but I'm just going to disregard that. It's probably not, the best to drop things out unless you're really sure that they're not needed, if it doesn't involve the parameters, if it's just x's, if it's just numbers, if it's just pi or something, then it's not going to be used. And this is s plus t times the log of 1 minus theta. So if you take the derivative of that thing, you get a q plus r over theta. And this is another example of a chain rule, s plus t over 1 minus theta. And there's a minus there. So I'll write that on the next page. The d log likelihood for theta in this case, there was a q plus r over theta, and then s plus t over 1 minus theta. And the chain rule gets another negative here. Set it equal to 0. If you put 1 on, add this to both sides, s plus t over 1 minus theta. If you multiply by theta times 1 minus theta, you'll get a cancellation over here, so you get 1 minus theta times q plus r. Over here, the 1 minus theta cancels, so theta s plus t. And you multiply this out, you get q plus r over here. And then you take everything that has a theta in it and add it over here. And there's q plus r plus s plus t, which is our total sample size at n. So theta hat finish is this q plus r over n. So that's kind of how that one works out. Now the solutions for the homework 4 problems are posted. Did you get any notice about that? So when I change it, it says there's a button I can click, like notify users of changes. So I did that for those last couple times. So I'm glad you are getting that. It doesn't come to me for some reason, so I don't see it. Not the lectures. Under the homework, this one, I've posted these solutions.
Those aren't up right now. Like I have it open, they're not up.
It's not on yours?
No, the solutions, so.
Oh. Let's see. Assignment. I didn't save it. Huh. It's not there. I changed the word. Let's see now. We can post it. So, file, I'm pretty sure I did go through this. Put it there. Lectures. So there, and then I have to click save. That's what. If you don't click save, then it's not. It doesn't keep it. Go back. It doesn't notify you. So hopefully that should be there.
Yeah.
Good. But in these solutions, so here's this first one, and I just follow the same pattern of writing down. I want the product of all the densities. I copy the density in here with the x of i's. The thetas combined. These things. You could do 2 to the n, and then you'd have a product of these square roots. Up in the exponents, you get a sum of the square roots there. So taking the logs, get n times log theta. There's a theta there, and then that other stuff is over there, which I've modified some. And the derivative is 1 over theta, just minus the square root of xi, and then that ends up being the solution. So that type of solution is there for the other one. I didn't take off too many points in the grading. If somebody, say, forgot to, I think this one was a couple, somehow the 2's in, I don't know. Anyway, it ended up being, yeah. Yes?
Would there be a problem on the test like the homework where it's like asking for the maximum likelihood like of 2 functions, that?
Yeah, I haven't written it yet, but we can look at that one. So that's kind of the same thing there. There was this one,
That one.
right, where you had n observations from this exponential and m observations from this exponential.
Yeah.
And the observations kind of clumped together. So you could very well imagine having small counties and big counties, and they're coming together, or big schools and small schools. I know that in Rockville, Maryland, when they were building new elementaries, their big build size is about 960 students in an elementary, and then but the smaller ones that they had before were in the 600 range. So they had two different sizes. That's going to affect the Poisson rate that's there. So this was kind of an interesting. A number of students found the MLEs for this sample. They found the MLE for this sample, and they knew they needed to do something with it together, so multiplied it together, or added them, or did something, or just reported them separately. But in likelihood theory, we put together all the data, the joint distribution of all the x's and all the y's. The x's are independent, the y's are independent, they're independent of one another, so it's just a big product. Product for the x densities, product for the y densities, and that's what you get. So when you combine over here, it's a lambda to the n, these are negative lambda, and the x's add together. In this case, there's the two lambdas and the two lambdas here, but otherwise it adds together. And then it's the same lambda, the same parameter. So the data combined together to tell you about it. Okay? So the 2's are here, there's lambda to the n plus m, and this lambda has the sum of, and this 2 continues, right? There is a 2 here. A couple of students dropped that 2 and just got the sum of x plus the sum of the y. But the y's are kind of areas that are twice as big, so they count twice as much, I guess. So, right, and that's the likelihood, so we can take the log. You do have this 2 there that will go away once you take a derivative, and m plus n times that. And this one, so you take the derivatives, you get 1 over lambda here, but that lambda just goes away. I set that equal to 0, and you end up getting this as the solution. If it is 2 densities with the same parameters, you just multiply them together and do that. So that's kind of the, you can practice writing out how would you describe some of the algorithms, how you describe some of the tests. Think about what the bootstrap means, what a permutation test is doing for you. And I think that the practice problems and the homework problems, that the ones that go on the exam will be pretty similar. Right? So you practice. So bring a calculator. Pen and pencil's fine. I'll give space on the sheet to write answers. And I have regular office hours tomorrow, or if you have quick questions and want to send an email, I can answer that later. You too.
Good day.
Two.